So the next thing we're going to move on to is what is referred to excitation contraction coupling, or in its fuller title, excitation contraction recoupling. And this is really explaining the connection between what we've been referring to previously within this video cast, which is the structure and function of the fibre, and that motor unit, and how that electrical signal that is coming in is in essence imparted into the fibre to generate the force, to generate the connection really between the actin and the myosin filament. And if we look at this statement from Stevenson in Acta Physiologica Scandinavia, it really summarises this up for us. Regardless of fibre type characteristics, the excitation contraction recoupling cycle in all mammalian twitch fibres is believed to involve the following sequence of events. Firstly, the initiation and propagation of an action potential along the sarcolemma and transverse T-tubular systems. Well, we've already learned about action potentials. Remember, action potential is quite simply the phrase for the electrical signal. 2, the detection of the T-system depolarization signal and signal transmission from the T-tubule to the sarcoplasmic reticulum membrane. Excuse me. 3, the calcium release from the sarcoplasmic reticulum. 4, the transient rise of myoplasmic calcium. 5, the transient activation of the calcium regulatory system and of the contractile apparatus. And 6, calcium reuptake by the sarcoplasmic reticulum, calcium pump and calcium binding to the myoplasmic sites. Oh my God, what is all this about? There's an awful lot going on here. But fundamentally, what it is referring to, as we're about to see, it is the connection between what is happening in terms of electrical signal coming in through the central nervous system, through the peripheral nerve, to the motor unit, which is the connection, or the motor end plate, sorry, which is the connection between the peripheral nerve and the muscle, and how that is converted into a chemical signal, and how that chemical signal is then proliferated across the muscle fibre to generate and help generate force. And so this is very much about what is happening here. Now, we've seen all this previously, but what you can see is that fundamentally is that the whole process is about the interaction between the actin and the myosin filament. And fundamentally, the key to this is using ATP. It's an ATP-dependent process. So everything you've been learning about in terms of systems physiology and metabolism really fundamentally comes down to this, that we are using ATP to generate the interaction between the actin and the myosin filaments. And without the ATP, and what happens is it's not, it's just ATP, it's the splitting of the ATP molecule that allows the myosin to pull on the actin filament. So we know that fundamentally there's a huge metabolic component to this. But how does that all kind of work? Well, the fundamental thing to understand is the myosin is not actually directly attaching to actin per se. That what you have got surrounding actin is you've got two real important structures. You've got what's called troponin and tropomyosin. And in fact, what actually happens is that the myosin head attaches to tropomyosin, which is embedded within the actin filament. But the tropomyosin is actually covered in a shield. And the shield is actually what is called troponin. And in fact, if that shield is in place, the myosin head will never attach to tropomyosin and therefore will never pull the actin filaments across. So how do you get that troponin, that shield, away from tropomyosin? Well, the key to this is what Stevenson was referring to in that previous statement, which is calcium. Calcium is the key regulating chemical here in terms of the generation of force. What happens is that the calcium, as we're about to see, will flood into the sarcomere. It will flood into the sarcomere, and the calcium will bond with the troponin, and only if it bonds with the troponin does that, it's like a lock and key mechanism, does that bond into the troponin allow the troponin to move out the way to reveal the tropomyosin, which is the bonding site. And then if we split the ATP molecule, the myosin head will the myosin head will attach to the tropomyosin, and that splitting of the ATP generates the force. But if there's no calcium, the troponin won't move. There will be no interaction between the actin and the myosin filaments, and therefore the myosin and the tropomyosin, which is embedded within that actin filament. So calcium is the fundamental key to this. So very much what we're talking about in this process is how do we go from an electrical signal, the action potential, to generating and releasing calcium, which is fundamental to this process, into the sarcomere to provide the unique environment for the muscle to generate force. But also, remember what Stevenson was saying. Stevenson was also referring to that statement about the reuptake of calcium. You've only got a finite amount of calcium. It's not just a case keep releasing, keep releasing. That calcium has to come back out in order to be ready for the next action potential. And that is what we're going to look at very briefly here in the idea of excitation, contraction, recoupling. And it's a very complicated process. I'm not going to dwell on this, but there's an awful lot that is going on, and you can see it in this schematic here. Everything from what is called the sodium-potassium pump, which you may well have heard of previously. And the sodium-potassium pump is really where we take that electrical signal and we start to convert that in the motor end plate into a chemical signal, through to the process and the propagation of our calcium ions across the sarcolemma, which we'll talk about in a moment, into the sarcomere, basically allowing for that connection between the actin and the myosin filaments. So we've got the 6 stages that Stevenson talked about. So let's start with stage 1, which is referred to as the initiation and propagation of the action potential. Remember, what's happening is that you're getting an electrical signal coming in because you need to innervate the fibre. So action potentials are just the posh term for that. Action potentials originate where? Well, in the neuromuscular junction, because they're coming from the peripheral nerve, in response to the release of acetylcholine from the nerve terminals. And they spread out from the motor end plate into the T-tubules. And the T-tubules are basically a structure that surrounds the sarcomere. It's like a matrix of kind of pipes and tubes that surrounds the sarcomere. The upstroke of the action potential is caused by the regenerative action of sodium channels, which repolarization results from the downregulation of sodium channels and delayed activation of the potassium. So this is very much what you may have learnt about, which is called the sodium-potassium pump. So to sustain an action potential, it is critical that the resting membrane potential does not fall below minus 70 to minus 80 millivolts. Otherwise, not enough sodium channels can be activated. So the key here is that we have to have a large enough signal coming in to generate a membrane potential to open the sodium channels. So that is where the whole process starts. We have to have a large enough signal coming in. It's interesting that it's referred to as a negative signal. It's still a signal, millivolts. It has to be large enough to open up the sodium channels to start this process that we're trying to generate. What then happens is, when the action potentials reach these T-tubules, and then remember the T-tubules is this kind of matrix of tubes that run around the sarcomere, this generates a wave of depolarization, and that is sensed by what are called multi-subunit structures. So under resting conditions, the sarcoplasmic reticulum, which is the cellular structure, under resting conditions, the sarcoplasmic reticulum calcium release channels are essentially closed. Why? Because there's an inhibitory effect of a chemical, which is magnesium. So magnesium, under resting conditions, prevents the calcium being released from the sarcoplasmic reticulum. And that makes a lot of sense, right? Because under resting conditions, you don't want to generate force. And if we go back to that basic overview, we said that the way you generate force is by releasing calcium, because the calcium is going to bond to the troponin to reveal the tropomyosin, which gives us the bonding site between the actin and the myosin filaments to generate force. So there's no good having calcium flooding into the T-tubules, because we don't need to generate force under resting conditions. But the depolarization of the T-tubules is detected by what are referred to as the DHPR complexes, and that is transmitted to the calcium release channels, reducing the affinity for magnesium. So in other words, what happens is that as we start to get the action potential starting to arrive, that is detected, and that basically down-regulates the inhibitory effect of magnesium. In other words, what happens is we start to open up the sarcoplasmic calcium release channels, and so because the magnesium is being basically down-regulated, it's basically being deactivated, it's being depolarized, it's going from being double positive charge, C++, to having no charge. Because that happens, because the action potential arrives, its kind of inhibitory effect disappears. That then allows calcium levels to start to rise. And remember I said calcium is the key to this process. Which brings us to stage 3. So now what we're starting to deal with is the way in which that the calcium will now start to be released from the sarcoplasmic reticulum. So the rate of calcium release from the sarcoplasmic reticulum depends on the number of sarcoplasmic release channels, how many are open, the average time that they're open for, and how big the gradient is across the channels. Let me explain what I mean. Fundamentally, there are three things here. We need calcium. We need calcium because we need calcium to bond in the end to the troponin to reveal the tropomyosin for the muscle to generate force, to get the connection between the actin and the myosin filaments. So clearly, the fundamental key here is how much calcium we can release into the sarcomere to get that connection. So the amount of calcium that comes in is going to be dependent upon how many release channels are open. If we only open 1 or 2, you only get a small amount of calcium coming in. If I open a lot of those channels, then a lot more calcium can come into the sarcomere. The second thing is, well, how long are they open for? So if they're only open for a small amount of time, so I could have 2 channels that are open for a long period of time. Okay, let's say they're open for 10 milliseconds, but then I have 10 that are opened for 1 millisecond. In fact, actually, I'm probably going to get more calcium coming if I've got 2 open for 10 milliseconds than if I've got 1 or 2 open for 1 millisecond, or 10 open, sorry, for 1 millisecond. So the average time that channels are open is really important. But then fundamentally, so is this, which is what is the concentration gradient between the sarcoplasmic reticulum, where the calcium is stored, and the sarcomere itself. We have to move from a high gradient to a low gradient. And this is really important, because as we start to generate more and more contractions, the time between the calcium coming back out, as you're about to see, coming back out from the sarcomere, back into its storage site in the sarcoplasmic reticulum, becomes shorter and shorter. And therefore, some calcium will still be in the sarcomere. And so the difference between the calcium in the sarcoplasmic reticulum, where it is stored, and the calcium that's in the sarcomere, that gradient would be slightly less. If the gradient is high, in other words, we've got no calcium in the sarcomere, we've got loads of calcium in the sarcoplasmic reticulum, then it comes out really rapidly. Really rapidly. So that is a fundamental thing. If we can get the calcium back out into its sites, its storage sites, then it allows us to have a bigger gradient, and therefore get the calcium out into the sarcomere more rapidly. So the average open time of the calcium channels could be reduced. Why? Well, you could reduce it maybe by decreased pH. So if pH falls, we've got, say, more hydrogen ions and we've got more ammonia, then that actually has a direct action on the release channels, and therefore they're not open for a long period of time. You can increase it by perhaps making it more alkaline in the cell, for example. But the average time is absolutely a fatigue component. So if you imagine that, you can understand that actually the average time that these channels are open is less in a fast fatigable fibre than it would be in a slow fibre. But the amount of channels that we have is greater in a fast fibre than it is in a slow fibre. So this is really important. It's understanding that these factors are fundamentally linked to the muscle fibre types as well. So then we come to kind of part 4 of this process, which is the rise of what is called myoplastic calcium. So now what's happening is the calcium is being released from the sarcoplasmic reticulum. Remember, that's where it's been stored. And it causes a rise in the myoplasma. And what I mean by the myoplasma is basically within the sarcomere of the fibre, within the cell structure of the fibre. And the magnitude of the time course of this rise is being a function of the interplay between the sarcoplasmic release and the uptake of calcium. In other words, how many channels are open, how long they're open for, and what that concentration gradient is. So fundamentally, the amount of calcium that we get into the myoplasm and therefore into the sarcomere is fundamentally dependent upon those 3 characteristics we've been referring to: the average time that the sites are open, the number of sites that are open, and that concentration gradient. So what has been identified in a study actually back in the mid-90s is that the rise of myoplasmic calcium represents 1% of the calcium which is released from the sarcoplasmic reticulum. So just 1%. So you're only dealing with small amounts here, right? So it's not like you're ever going to run out of this. And the peak of the calcium would appear to occur before the generation of tension in the muscle. But the decrease of the calcium has far faster kinetics than the time course of the force response. So in other words, it's not a case of the calcium comes in, you generate the force. What it's telling you is the calcium comes in, it provides the environment in order to create the environment for the interaction between the actin and myosin filament. It's not a case of the calcium levels go up, bang, we get the generation of force. What happens is that the peak is reached, and only after that peak is reached, and therefore we get the interaction between the calcium, the troponin, revealing the tropomyosin, will we then generate the force itself. It's not one thing is actually sitting on top of the other. Which then brings us to point 5, which is the activation of the regulatory system in the contractile apparatus, right? So when you've got resting levels of calcium, the actin and myosin filaments don't develop force. Why? Well, partly, remember that we said that magnesium has an inhibitory effect of calcium release. So in other words, there'll be no calcium sitting in the myoplasm. Therefore, if there's no calcium in the myoplasm of the muscle fibre cell, there's no calcium to bond to troponin, and therefore you cannot get that tropomyosin site being revealed. So no generation of force. But when it's raised, it removes the inhibitory effect of the calcium regulatory system. In other words, when you get that sudden surge, remember we said that what happens is as the action potential comes in, that down-regulates the magnesium. We get a brief rise in the calcium concentration. Therefore, we are then able to get the interaction between the calcium and the troponin to generate the tropomyosin binding site. So the calcium now binds, as we've been referring to, troponin, reveals tropomyosin, and then what you've now created is the actin binding sites for the cross-bridge interaction and force generation. And you can see this here. This is quite nice, right? So what you can see is as the calcium concentration increases on the x-axis, the relative force also increases on the y-axis. Okay, so you can see that at any given point on that graph. So as the amount of calcium that we have available increases, so does the amount of relative force that we're going to produce. And then we come to the final point, which is, remember, you've got to get the calcium back out, because the calcium is sitting in the myoplasm, then the concentration gradient between the sarcoplasmic reticulum, where it's stored, and the myoplasm would either be the wrong way round. It would either be too much in the myoplasm of the cell, or it would be almost equilibrium, and therefore you wouldn't be getting calcium being pumped back in. So for the muscle to fully relax, that calcium must be resequestered. In other words, it's got to be pumped back into the sarcoplasmic reticulum. By pumping it back in, the calcium levels in the myoplasm, in the sarcomere, decrease. And it's a pumping action. And it uses what's called the sarcoplasmic reticulum calcium pump. So what happens is because the concentration is high, what it does is a very clever system, is as the concentration reaches kind of a peak within the myoplasm, that then prevents the release of any more calcium from the sarcoplasmic reticulum. And when it reaches that kind of peak concentration, it then automatically activates its own pumping mechanism and drives the calcium back into the T-tubule systems, back into the sarcoplasmic reticulum, prior to the next action potential arriving. And so what you have is excitation, action potential coming in, excitation, contraction, that is the interaction between the calcium, the troponin, the revealing of the tropomyosin, excitation, contraction, recoupling, where the calcium is being pumped back out into the sarcoplasmic reticulum in preparation for the next action potential arriving. And in fact, if we look at this statement here, again, this is from the paper that we've referred to earlier from EJAP, the rate of tension development is faster in type 1 than type 2 fibres. This phenomenon is related to type 2 fibres having a greater total calcium release per action potential and a faster time constant of calcium currents, as well as fast myosin, troponin and tropomyosin isoforms. Right, so what they are saying here is what we've been referring to is that basically what happens in a type 2 fibre is there's more calcium. And so what's happening is more channels are going to be open, so you get a greater calcium release, and the average time those fibres are open is going to be greater, and we're able to get probably a greater concentration gradient between the calcium channels and the myoplasm. And fundamentally also what is interesting, which we won't deal with in this lecture, is there are actually what are called fast forms of myosin, troponin and tropomyosin. They operate slightly differently. They are able to work their muscle magic, I suppose, at faster rates than slow twitch fibres do themselves.